And with that being said, what better way to begin than with the problem I've recently been working on? How do we determine the region visible to a virtual camera? For this solution, a uniform grid of n by n cells will be used to evenly divide the world into its minimum and maximum components. In this particular example below, we can determine that as far as this grid is concerned, we are only interested in cells 1, 3, 2, 0 to 2, 3, 3, 0 to 3, 3, and 4, 1 to 4, 3. This now poses the question, how do we determine the cells that are visible? The key observation to make here is that the frustum edges themselves are lines that pass through the cells bordering the visible region. It does say depth set here, but you can mentally retitle this to be the boundary set, since it is the set that contains the one-dimensional hash values of the grid cells which the frustum boundary lies. And we can see that down here. These boundary cells can also be broken into their two-dimensional components, their x and z, and used to record the minimum and maximum x values for a given z. By mapping the z values to their x range, we can encode the visible grid cells in a map called the depth range table. For example, if we were to start right here and go from the beginning of this line towards the end, we would see that it's a line that goes from 4, 3 to 1, 3. So checking the depth of 3, we in fact see that has a range of 1 to 4. The actual algorithm to do this is rather straightforward. Given a beginning and an endpoint of a frustum edge, we can use the parametric equation for a line, p prime equals p plus vt, to take tiny steps from that beginning point towards that endpoint, and then anywhere we are along that line during the march, we can take the 1 and 2 dimensional values and record it for that particular point. When we retrieve a new one-dimensional cell value, it is included into the boundary set, and when we have a new z value for the depth range table, its current x is recorded as the min and max range for that z, and once we repeat that z, we update the x to potentially reflect a new minimum or a new maximum value. By repeating this process for every line in the frustum polygon, the boundary set and the depth range table can be built together. A quick note about why height can be discarded at the moment is because we are only interested in the x and z plane that the frustum polygon exists in. So long as the points that we are testing visibility against exist within this range, they are potential candidates for visibility anywhere within the y-axis. This is also the reason why, even if only a tiny part of a cell is taken by, or a tiny part of a cell is crossed through by a line, the entire cell is taken. So now that we have the algorithm to determine the cells we care about, how do we actually go about getting the frustum polygon to march along its edges? The main thing we take away from the last slide is the fact that we are reducing planes into their 2D analog lines, or more specifically, edges. Although the exact values in world space might be unknown, in camera space, the planes making up the frustum polyhedron are known to have fixed normalized combinations of the components that make up the camera's projection in view. For example, the near and far plane in camera space are always known to point up and down the z-axes and have a distance of their respective near and far values from the origin. A less simple case are the left and right planes. They carry the combinations in the x direction of the positive or negative focal length, nothing in the y, and in the z they carry the aspect ratio. And of course these values are once more normalized to give the normal of the plane. However, because we know that the near far and left and right points of the standard view frustum lie on the respective near and far planes in camera space, we can transform the points out of camera space and back into world space using the world space matrix of the camera. And now that we have the world space min and max xz extents of the frustum polygon and world space, the aforementioned algorithm can be easily used using these 4 points to generate the typical 4 frustum polygon edges. And now, of course, as with all things in life, there is always a caveat, and this one is actually the Frustum polygon itself. Since the world space is technically an infinite region, the grid acts as a clipped out region of finite space, which we have the tools to reason about in. By treating the bounding edges of the grid as their own planes, we can align border clipping planes to their respective axes and distances from the origin. Then passing the standard Frustum polygon through the north, east, south, and western clipping planes, should any part of the Frustum polygon be clipped, the resulting clipped polygon will be forced to be within the confines of the world grid. And as some of the astute amongst you may have noticed, that this is not actually the near plane, but rather this is in fact a clipped Frustum edge. In our particular example, the Frustum polygon that we end up doing the grid clip test against has 5 edges. This isn't really an issue though, because the algorithm will find the boundary cells and the depth range table for any given polygon. So now I think it would be useful to look at some code, and as previously mentioned, we're going to be using the world space matrix of the camera to transform out of camera space and into world space, and we get this by taking the inverse of the camera's view matrix. The next thing to notice is this movement out of camera space and into world space. At first glance, it may seem like a weird camera world space combination, but we're actually just moving out of camera space and into world space. The reason this happens is that the points on the camera space plane are transformed with respect to the plane, which means that it transforms with respect to normal vectors and not ordinary vectors. Basically what that means is that the planes are created in camera space using reciprocal values of the world space matrix that the camera used to create its view matrix. By inversing the view matrix back into the respective world space matrix of the virtual camera, the points are also transformed out of their camera space reciprocals and back into the world space points. The next part of the code I would like to look at is generating the Frustum polygon, clipping it, and generating the boundary set and the depth range table. So as you can see, the ordinary simple 4-edge Frustum polygon is created from these 4 points, and then we simply loop over or step through the north, east, south, and west bounding planes of the world grid and potentially clip that original Frustum polygon against each of these planes. Every time we just update the current Frustum polygon to be the clipped polygon, and we repeat our test until we're done with each of the 4 clipping planes. If we didn't clip the entire view polygon, meaning it wasn't facing right on one of the boundaries, we're going to loop through each of the polygon edges, and for each edge we're going to generate the Frustum boundary. So this is that algorithm that gives us the boundary cells and the depth range table. And as previously mentioned, we are starting from the near and working our way towards the far. And we do that by making sure that the distance from this point to the near squared is at least not greater than the distance from the far to the near, or the near to the far squared. Just a little note about why we use the squared magnitude instead of the normal magnitude, that because these are all linear combinations of numbers along the line, it doesn't actually matter which scale we give it. So we can give it a squared scale or we can give it a square root scale, but either way, whichever is larger will always be larger in this case. Or in this case, we're making sure that we're not larger than this line. So the actual algorithm just goes through and it gets the one-dimensional hash of the current point of the line. If it's new or if it's not in this current set, it gets inserted. If it's already in the set, nothing really happens. Then we go ahead and get the two-dimensional hash values for, or grid values for this point. We go ahead and check to make sure that the depth value of these two dimensions hasn't been previously encountered. If it hasn't, we just simply record the depth and we record the range. If it has been encountered before, we need to make sure that our current x is not less or greater than this range. And then when we're done with this loop, we just simply step along the line, generate our new point, and continue until this condition here fails. So the next thing I would like to show is just a quick demonstration visually of what the grid clip test actually looks like. So as you can see here, this is our Frustum polygon in green, and if we run it along the edge, we can see it gets clipped. And right now there is no options to call anything. So there's no Frustum Culling and there's no grid cell clipping. So the first thing we're going to do is turn on the grid clip, and we can see that immediately any cell which the Frustum passes through is included, and any cell that is not, or the Frustum does not pass through, is excluded. This is probably the biggest benefit to Framerate between Frustum Culling and grid clipping. But next I will actually show you Frustum Culling. Now that we are able to determine what cells are at least partially visible by the camera, we can focus on the second part of visibility, and that is culling. Before culling, the data has to be partitioned into one of two cases, either those that are on the interior or fully visible, or those which are along the boundary and partially visible. In the case of an interior cell, this is very simple. We just loop through the states associated with that cell, transform those states into model matrices, associate those model matrices with the mesh that that state was belonging to, and store all that information for the renderer. In the case where the cells are along the boundary of the frustum, the cell containers having the bounding volumes for their geometries are used to build up visibility BVHs. After the partitioning, the boundary cells are looped through once more, and this time the actual frustum cull is performed on the BVH blocks for the cell. Any bounding volume belonging to the renderable geometry found to be visible has its BVH ID recorded for the mapping back to the visible state, and I will explain more about that later. So the next parts of code that I would like to show are the partitioning and the culling. So first partition, as you can see, we just loop through the entire range for every depth in the depth range table. For any given x and z combination that we come across, we hash the world space position of the cell and check if this hash was previously determined to be a boundary cell. If this is a boundary cell, we simply start at 1, and using that as the starting ID, insert each of the bounding volumes, in this case they're spheres, into BVH blocks at this cell in the grid. Alternatively, if the cell was just an interior cell, the entire cell is assumed to be visible and only the states are collected for rendering. Technically, Frustum Culling could still remove some interior geometry, but it shouldn't really ever be close enough to the clipping plane en masse to warrant the entire cell having the complexity of building up its own BVHs. So this is just a decision where I choose to render maybe a little extra at the cost of not building potentially wasted BVHs every time. Now, once the partition is complete, we actually loop over the boundary cells one last time, and for each either complete or incomplete BVH block, we go ahead and call these BVHs against the Frustum polyhedron. And as you can see, the actual Frustum call is a very simple one node descendant BVH collision check. We do our collision, or in this case visibility check. If it fails, we just get out of there. If it doesn't fail, and this was base geometry, we're going to store that ID, and I'll talk about this ID again soon, and we return. If we were visible, but we weren't a child, we just simply keep going down until one of these two hit return. Once we're all done, we return back the entire list of all visible volume IDs for that given cell. And then we go through the list of visible IDs, and we are going to pull out the state that corresponds to that cell. Now, just as with the grid clip, I will go ahead and show a quick demonstration of the Frustum call. So to jog your memory, here's the grid clip. You can see we get just the cells that we care about, but we get extra geometry that we don't care about. And now we'll go ahead and turn on the Frustum call. Now we see we get only the geometry that we truly care about. So one last thing I would like to mention before I go and show the full demonstration of performance gains, and I've kind of alluded to this with the way that the BVH IDs map up or match up to states, but really the key to this algorithm comes down to the packaging of data. Since the state and bounding volumes are tightly packed together per cell, they're only ever processed together. And by doing this, it gives you a much better advantage from the CPU cache because the containers are not stepping over one another. They're not grabbing needless data, and they're really only looped through once. Sometimes we don't even loop through them at all. If the cell is invisible, we just skip it. If the cell is fully visible, we skip the entire bounding volume container. And if the cell is partially visible, we process the bounding volume container first, process the bounding volumes, then process the states. All of this is greatly benefiting the CPU cache because it's very hot code, very hot data, but it's all packed very, very tightly together. And this is actually why the states and the bounding volumes are paired the way that they are. When the simulation is producing the data for the renderer to consume, the bounding volumes and their corresponding states are put into their respective cell containers at the same time, essentially meaning that bounding volume 0 is the bounding volume that describes the geometry at state 0. And state 0 describes the orientation and translation of bounding volume 0. So these are the two containers that describe all the information we care about. By mapping them together, we can start at 1 for the bounding volumes because 0 just means it's a parent. And then any volume that was visible, by reducing its volume ID by 1, we now have the state index that that visible volume corresponds to. So now I would like to go ahead and demonstrate the performance boost that grid clipping and Frustum Culling gives you. So currently we can see we are getting around 1800-ish FPS. If we go ahead and turn on just the grid clip now, we see we go from 18 all the way up to close to 5K. because we have heavily reduced how much geometry we actually even need to draw. And this is why I said that the grid clip actually provides you an even bigger boost to the Frustum Culling, because this is where you're going to see the largest percent gain. However, Frustum Culling itself still has some benefits to give. So you can see we are consistently now peaking well over 52. We're at 53 there, almost 55 there. And just to give a static comparison, just about 1800 again. Go to grid clip. We'll go to just around 5200. And now we will Frustum Cull. And we see it goes up to just around 5400-ish there. Thank you all for your time. I hope you were able to take something away from this, or you just at least enjoyed it. See you guys in the next one.